Today we're going to talk about developing kinematic formulas. Now the word kinematic simply means motion. So these are formulas that deal with motion. So we have a few of these formulas already. You recognize, hopefully, the acceleration formula. That's a kinematic formula. If I get even simpler than that, we had a formula that we used for something that had constant velocity. All right, so to get the average velocity, we can take the total displacement and divide it by the total of time. We've also taken this formula and developed a third kinematic formula by solving for VF, and we said VF equals VI plus A times delta T. That's a kinematic formula also. So when we look at kinematic variables, there's essentially 5 of them. There's 5 kinematic variables that you'll see in every situation where something is moving. If you look at this formula and this formula, these are both for accelerated motion. This one isn't. You never use this formula if you actually have acceleration. So if I think about the 5 variables for accelerated motion, what do these two not have that formula does have? Well, if I look at them, it's delta x. We need a formula that's going to handle accelerated motion and include delta x. So it'll tell us how far we might move if we're accelerating. So the way that we can do this is, I want you to think of if you have 2 different velocities. All right, you had an initial velocity and a final velocity. If I were to calculate the average of 2 velocities, how would you do it? How would you do that if you were averaging any 2 numbers? Well, I think if you really think about it, you're going to say, well, I'm going to add the 2 numbers together, and then to average them, I divide by 2. That's exactly what we're going to do to get this new formula that we want to talk about. I'm going to say that if I want to know what the average velocity is, that I'm going to take the initial velocity plus the final velocity, and I'm just going to divide by 2, like I'd average any 2 numbers. All right, so I know the average velocity is going to equal this, but we also already know that average velocity equals this. It would equal delta x over delta t. So if this equals average velocity and this equals average velocity, then these two must equal each other. All right? So I would say that delta x over delta t equals 1/2. I didn't want to leave the fraction here. I'm going to go ahead and pull it out. So I hope you guys can see that this is exactly the same thing as that. So if I want to make an equation then that's going to solve for delta x, all I have to do is multiply both sides by delta t to isolate delta x. And what I end up with when I do that is going to be delta x equals 1/2 vi plus vf. And when I multiply this equation, multiply both sides by delta t, I get rid of it here, but I have to end up with it over here. So we have now a third accelerated kinematic formula, which would be delta x equals 1/2 vi plus vf times delta t. So that's our next kinematic formula. And what I would call this is displacement with constant uniform acceleration. So what does that, I'm going to move over here in this space. What would that mean? Well, it's simply constant uniform acceleration just means your velocity is changing, but it's changing the same amount every second. It doesn't go like real fast and then taper off a little bit. It's going to have the same change every single second, a lot like gravitational acceleration does. As we look at the formulas that we've developed, hopefully you can notice that there are certain variables that you see all the time in a motion problem. And there's 5 of them, and they're always the same 5. So the reason why this is important is this means when you're solving a motion problem, you're always looking for the same 5 things. Right? This isn't a big mystery or anything. You can identify them right off the bat. I mean, I know what 5 they're going to be. It's just a question of whether or not I have them. So if I look at the formulas, and let's not considering this one, because this is not an accelerated formula, all right? But the other 3, what are the variables that you see that we see listed in these all the time? Well, one that I see is acceleration. We always see acceleration in this formula. We always see VF in these formulas. We always see VI in these formulas. If I'm just looking at the top one, the acceleration formula, I always see delta t. And the new one that we just looked at, I'm always going to see delta x. Now, it's going to be delta x if you're working horizontally along the ground, but we'll also see we can solve problems where the movement's vertical. Instead of delta x, we call it delta y. But you would use it in the exact same place in a formula. All right, so these 5 variables are always found in motion formulas, okay, in kinematic formulas. But what I want you to notice about the 3 that I have listed up there, again, not the average velocity one, but the other 3, is that I want you to look at them. Do they have 5 variables in them? Do they have all 5 of the variables that I just described? No. If you look at them, none of them do. This one only has 4. So does this, and so does this. Now, if I'm solving a problem for one of these 5 variables that are up here, each of these equations only have 4 variables in them. How many would you actually have to know in order to solve for the one variable you're looking for? Well, if I think about it, these all have 4 variables. If I just know 3 of those 5, if I know 3 of them, I know immediately, I know immediately that I'm going to be able to solve that problem. So this goes for any problem that deals with motion, in particular accelerated motion. If I know 3 of those 5, I'm going to be able to solve it. I'm going to have an equation, a kinematic formula, that will allow me to solve that thing. So if you look at this, what I commonly will do is I will figure out what I know and what I don't when I solve a problem, and then I look to an equation. And I don't look for the stuff that I know. What I'm actually looking for is the one variable that I don't know, but I really don't care about. So, for instance, if I go back to this, if I look at this formula, which of these 5 are missing? Right? Which of these 5 are missing from this formula? Well, if I look at it, these are all in there. The one I'm missing is delta x. And so in the back of your comp, what I would do is I would write next to each of these formulas, I'm going to say no delta x right next to this one. That means if I'm looking for a formula that's going to solve for one of these, and I don't know what delta x is, but I don't care, that's my go-to. All right, this formula here came from this one. So what's this missing? Well, it's also going to be missing delta x. A lot of people get stuck on, oh, what formula do I use? But the point here is you're not really looking for what you have. You're looking for the one thing that you don't have, but you don't care about. Okay, and as I go over some examples, it'll be more clear. How about this one? What's missing out of this one? The one that we just did. What's missing here? If you look at it closely, the one thing that is missing is there's no acceleration. Acceleration's not in there. So what we did when we developed that formula is we basically got rid of acceleration. Okay? So you're gonna notice as we go through the rest of these kinematic formulas, it's always the same 5 variables. The formulas themselves only have 4. And the one thing you need to do is you only need to know 3, because that 4th one is going to be the one you're solving for. So we have formulas at this point, kinematic formulas, motion formulas at this point. We've got one that has no delta x. We've got 2 that have no delta x. We've got one that has no a. If we think about these formulas then, I would like a formula that has, for instance, no vf. What if I don't know what the final velocity is, but I want to solve for one of the other variables, one of the other of those 5? So we're going to develop a formula right now that is displacement with constant uniform acceleration. Now, this has to be true really for all of these, is that the acceleration, remember that's a change in speed, has to be constant, and it has to be the same all the time. So free fall acceleration is a good example of constant uniform acceleration. It's 10 meters per second, or for AP physics, we commonly will use 9.8 meters per second squared. All right, it's the same. Every moment that something falls, you have that same acceleration. That is constant uniform acceleration, or you'll hear me call it KUA sometimes. So the way that we're going to work out these kinematic formulas is they're all related to each other. So I'm going to use one of the formulas we already know, and I'm going to work a substitution into that formula with one of the other formulas that we already know. So one of the formulas I'm going to use here is this one, the one that we did earlier in this video. Delta x equals 1/2 vi plus vf times delta t. I'm also going to use the formula which one was the other one? I was going to use this one, vf equals vi plus a delta t. Now, I want you to notice that both of these formulas have vf in them. They both have vf. And this one solved for vf. Well, what I can do here is I'm going to take this formula, substitute, and we're going to substitute for vf into this formula. So this becomes delta x equals 1/2 vi plus, now here I'm going to substitute this in for vf. All right, I'm going to take this and substitute for vf, so that instead of having vf right here, I instead have vi plus a delta t times delta t. All right? So notice that substituting this in for vf basically serves the function of removing vf from the equation. vf's not in there anymore. If I simplify this, I'm going to end up with delta x equals, I'm going to go ahead and simplify what's inside of those parentheses. This is going to be 2 vi, these two added together, plus a times delta t, and then times delta t on the outside. Okay? Let's go ahead and distribute the delta t and the 1/2. So I'm going to have delta x equals 1/2 times 2 vi. The 1/2 cancels the 2. So all I have left with there is vi times this delta t, because I need to multiply that in also. So I'm going to end up with this. Now, before I get too much further, these kinematic formulas, you guys, you're going to have to know how to use them. You're not going to have to derive them like this. I'm just showing you in this video how this works, that all these equations came from somewhere, and they're all related to each other. Okay? So when I distribute this here, I get vi. If I distribute the delta t in there also, I get vi times delta t. Plus, the 1/2 times this gives me 1/2 okay? The A, nothing really happens with the A here, but the delta t also has to be distributed, and so when we distribute that, we get 1/2, right, A times delta t squared. And notice this squared only applies to the delta t. All right? This is your formula, which we will call displacement with constant uniform acceleration. All right? That's what this formula is, and it should go in the back of your comp book. Okay? That last page, you should be putting this in the back of your comp book. All of these should go in the same general area, and you'd call them kinematic formulas. Now, what's missing here? Just like I wrote know this, know that over there, there's something else that's missing here. This one has no VF. All right, so if I'm looking at a problem and I don't know what VF is, I can use this to help me out. All right, if I don't know VF but I don't care about VF, this is my go-to. Now we need an equation that has, if you look at what we have here, I want an equation that has no delta t in it. So if I don't know how long that something is accelerating for, or if I drop something and I don't know how long that it's going, I can use a formula that has no delta t. To do this, I'm going to start with the same formula we did before, which was delta x equals 1/2 vi plus vf times delta t. I'm also going to use the acceleration formula. A equals, this is vf minus vi over delta t. Okay? Now, if I want a formula that has no delta t, I need to get rid of delta t. So I want to take this equation. Here's my plan. I'm going to take this equation. I'm going to solve it for delta t. Once I do that, I'm going to substitute that in for delta t in this equation. And that'll basically mean we get rid of delta t. So if I solve this for delta t, I would multiply both sides by delta t to get rid of the fraction. So I'll just say I'm going to multiply both sides by delta t. Okay? That gets rid of it over here. But then I want to have delta t so it's all by itself here. So then what I would do is I would divide both sides by a. Again, you guys, you don't have to develop these formulas on your own. That really goes for the AP test, although there are times that you will have to take two formulas, just like we're doing here, and make that substitution on the AP exam. All right? It's not uncommon to see a question where you have to do that, so this is kind of practice for that. Well, if I look to see what I have here, the delta t cancels on that side. The a cancels on this side, and I end up with a equals vf minus vi over, oops, I did that wrong. Let me get rid of this, because all that really happens here is in the original formula, the a switches places with the delta t. All right, you got delta t left here. The delta t cancels here and leaves a on the bottom. So I'm going to make a substitution of this into this. So I'm going to substitute into that equation. My equation here then will say delta x equals 1/2 vi plus vf. And then we're going to substitute vf minus vi over a. I'm going to kind of keep them grouped together. Okay, to make an equation out of this, it looks like kind of a mess. The first thing I'm going to do is, I hate fractions. I want to get rid of them just as quickly as I can. So I'm going to multiply both sides by a, all right? That would give me a, or delta x, times a equals 1/2 Then what I'm going to do, because I've gotten, well, you know what? I don't want to do it in multiple steps like that. Just to make sure it's clear what's happening. I'm going to end up with that after I multiply both sides by a. All right, the next thing I'm going to do is multiply both sides by 2. Let's get rid of this 1/2. If I do that, I'm going to switch these around because I like the way it looks better. 2 times a times delta x. If I multiply both sides by 2. If I multiply this side by 2, the half just goes away. Now you guys, I don't remember what you call it in math. I think it's difference of squares or something. I don't remember. But if you FOIL these two, okay, if you FOIL these two, you end up with VI times VI is going to give you VI squared. All right, because it's plus and minus, you could flip these around if you want. Because it's plus and minus, the middle term gets knocked out. The VI times VF, okay, if I do this, and then I do this, one's positive, the other's negative, it wipes out. Then I'm going to, finally I'm going to do this, which I basically see is going to be VF squared. So this equation in the end is going to be for final velocity. All I need to do to isolate final velocity then is move the VI squared to the other side by subtracting. My final version of this equation then is going to look like so. VF squared equals, when I move that over, I should be subtracting it. I should be getting, I made a mistake here. This shouldn't be VI squared. This should be negative VI squared, like so. All right? So in order to get rid of the VI squared, to move it away to the other side, because I want to isolate VF, that's the name of our formula, I would have to add it to both sides. When I do that, I get this. Positive VI squared when it's added to this side, plus 2a delta x. Guess where this is going? Back of your comp, all right? This is your back of your comp. Now, most importantly to me is, what did I get rid of? Which of the 5 variables did we get rid of here? Well, if you just look for what I substituted for delta t. That's what's missing. So this one has no delta t. All right? This one has no delta t. You want to put that in the back of your comp with no delta t right next to it. So we've developed a number of different formulas at this point that we can use to solve motion problems. With these formulas, you can solve almost any problem involving accelerated motion that someone throws at you. You just have to know what the tricks are, and you'll no longer be afraid of word problems once we do that. So we're going to start going over some examples in the next video so you can see there are definite steps that you do every single time with these problems. That's why you shouldn't fear these type of motion problems from physics.